Here we go, Lecturette 8. The illusions are up to you. And again, I think we're kind of in the part of the semester that kind of represents the doldrums. We were talking in our lectures meeting, our lecture Zoom meeting yesterday, that, you know, God, we're almost halfway through the semester. It's hard to believe. And I know that the doldrums kind of hit us at that point in time. There's not much in the way of breaks this semester. We're kind of going to push straight through. Was the academic calendar. So let's have a little fun and maybe augment our understanding of the processes that are before us. In this case, we're going to be contributing to a discussion board, again in pairs, so it's his team level assignment. And I'm going to call it The Illusions Are Up to You. And so I'm interested to see what you guys come up with. Let's talk about visual perception and sensation. So the anatomy of the eye, pretty straightforward. I'm sure you guys are well up on this. But then we have, you know, a stimulus object, and we're going to talk about how this becomes the source of stimulation for the visual system, right? And the light reflecting off is represented as electromagnetic energy. It's going to enter the eye. The iris then can control the amount of light, and the cornea and the lens do the focusing of the light, and then the light is eventually, it winds up on the retina, where the rods and cones, that is the sensory mechanisms, measure the light intensity and the light quality. So there's two processes that are going on. So that retina then is the light sensitive layer at the back of the eyeball, and that's where the photoreceptors are located. And photoreceptors are simply these cells that are sensitive to either the quality of light or the intensity of light, right? So rods do the work of judging the intensity or assessing the intensity, and then cones then are sensitive to the color quality of the light. The fovea, of course, is the sharpest area in the center of the back of the eye, just above the optic nerve, which is going to carry the transduced signals. Remember the transduced signals. So we have the electromagnetic energy entering, right? And let's take a look at that. So what we have, the lens is, you can't even see, is way over here, but we have the incoming light focused electromagnetic energy, and it's going to hit the back of the retina, and it activates then, based on its quality or intensity, the rods and the cones, the actual photoreceptors. And you can see how they're arrayed, and what happens is then you have bipolar and ganglion cells that in fact integrate the messages. If this didn't occur, we'd have a real confusing issue. So the rods are very sensitive, but they don't detect color, and I want you to consider this number astounds me. It's like when we talk about the brain and the number of the neurons in the brain, but if we just look at the eye, and notice these are neurons, they're receptor neurons. So these, all senses rely on receptor neurons, specialized neurons that transduce energy into neural impulses. So these guys are, once they get enough light, or a certain quality of light affects them, they do their firing process and they send the neural impulse. So it's at this magic moment that energy from the outside world becomes a neural impulse. That's where the transduction takes place by these specialized neurons called receptor neurons. Now, consider the eyeball. We're not talking a huge object here, and you know the proposed count is maybe 120 million rods or so arrayed on the retina. That's a huge, that's like a third of the population of the United States stuck inside your eyeball, all standing there next to each other. The scale is so enormous that it's not even really understandable when you think about it. Now, cones are less sensitive, right? They detect color, and there's 6 or 7 million of those, so far fewer cones, and you say, well, okay, so we are well adapted to light intensity to a certain extent, assessing light intensity, or highly dependent on that. Color intensity, maybe not so much, but think about it. When we look at a creature like a bee, a honeybee, right, they have color detection abilities that far surpass ours. But let's face it, bees deal in color, that is flowers, So it is a big deal to the bee. And if we look at the actual surface, if we use an electron microscope kind of image, we can see here the rods and cones arrayed on the retina. Excuse me for a second while I watch Willie try to climb out the third floor window. Willie, get down. Oh, sorry about that. I've opened the windows in the house, right, and that always makes the cats crazy, especially if the breeze is blowing. They're just all berserk today. So, what do we know from this? Lots of photoreceptors in the eyeball favoring the rods, but and now the difference between rods and cones and neural convergence, that is, note when we look at this, we see that multiple rods and cones are being fed to bipolar and ganglion cells. If we to have 120 million nerves stretching back to the optic processing center in the back of the head would be untenable. So the signal is condensed, right? So what do we know then? Well, the schematic diagram, it illustrates there's much more neural convergence between rods and ganglion cells than between cones and ganglion cells. And I think the rod has an easier job of it. The rod is just saying, hey, this is how intense the light is, right? The cones are reporting on color quality. There's fewer cones, so you can see how this system makes sense, right? So let's talk about how color is produced. Photons, that is waves of energy, and I'm going to get to that in just a minute, such as those projected from the sun, but any light source, if you will. And beyond that, when we look at the electromagnetic spectrum, we can see it's broader than just that. Pigments absorb some wavelengths of energy and reflect the wavelengths that are not absorbed. So in this idea, let's take a look at this shirt. We have this bright red here, and what this is saying is, as the electromagnetic energy comes to my shirt, the pigments in this shirt then absorb all wavelengths of electromagnetic energy except those represented as red. So everything is absorbed here and red is reflected. So only electromagnetic energy conforming to the red spectrum is reflected towards your retina, and that's why you're interpreting it as red, right? So it's the wavelengths that are reflected are the wavelengths that we sense. Black absorbs all colors, and that's why it appears black. That is, black is the absence of color. And if black is the absence of color, then what is white? White is a reflection of all the colors. Willie is going back for the window. Fortunately, it is not open enough for him to get out, but he's just a maniac this morning. Okay. Willie has half the rods and cones of most cats because he only has one eye. Believe it or not, we have two cats with one eye each. So Willie and Penelope are both our one-eyed cats, right? How common is that? So let's take a look at the electromagnetic spectrum, and this just blows my mind. Electromagnetic energy, really the quality of electromagnetic energy is determined by the distance that the electromagnetic particles travel from each other, the wavelength. So there's two qualities to electromagnetic energy. That is the distance between the waves, the peaks of the waves, and then intensity is determined by the height. But the quality is determined by the distance. So you guys, that are up on your physics, you know this already. And what I find fascinating is radio waves are these huge waves, peak to peak, right? Could be a couple thousand feet from peak to peak. Right? And so radio waves. Microwaves, and notice that we use microwaves in the oven. These wavelengths are already getting pretty small. They're about the size of the ant. So the microwave oven actually produces the microwave energy, the electromagnetic energy, and what it does is it hits the food, right? And it hits the food and it causes the food molecules to vibrate. It's hitting, right? Causes it to vibrate, and vibration, right? If you rub your hands together, right? The friction, what does it do? It produces heat, and that's how the microwave cooks food. That's fascinating in and of itself. And that's why when we microwave food, notice it gets hot on the outside before it gets hot on the inside, because the microwaves aren't actually penetrating the food. They're causing friction at the surface, and the heat has to work its way in, so to speak. Now, infrared, right, the wavelengths now are getting pretty tight. They're getting really small. But where we're interested here is in the visible spectrum. And if we blow out the visual spectrum, we see the waves are measured at this portion of the spectrum in nanometers. And 700 nanometers, so light of 700 nanometers would be very similar to what's being reflected off this shirt. And the 700 nanometers, and what the cones are doing, cones that are sensitive to light in that range, right, 700 nanometers become activated, whereas cones that are tuned to other wavelengths are not necessarily activated at that point. And you can see the color spectrum then. So red is 700 nanometers, all the way down to violet or indigo is 400 nanometers. How many of you are photographers, right? If your hobby is photography, then you probably know something about this. Especially like me, an old school photographer who was a film photographer, we would use filters, right, to change the quality of the light. And it makes a difference in black and white film as well as color film, interestingly. If you want to darken the sky and have your white clouds pop out, right, in black and white photography, what do? You use a red filter. Use a red filter because it blocks the blue light. And if it blocks the blue light, then blue light doesn't reach the film and the sky registers then as blackish, right? And then the white clouds, that energy is allowed to pass through, right? Become brighter on the film. So and then we go on down. X-rays, well, man, these guys are so narrow. Their little peaks and valleys are so narrow that they now go right through us. Remember, microwaves stay at the surface. X-rays are so narrow that they penetrate, and that's why we use them to take images inside people's bodies, because it will penetrate the outside surface and is blocked by denser material like bone. And then finally, what do we know about gamma rays? Bad news, right? When we're talking atomic radiation, this is gamma rays, and these penetrate virtually anything. They just blow right through you, and you can see the size representations. Anyway, we know about wavelengths now, and we know that the color spectrum is represented by 700 to 400 nanometers wavelength, right? Well, subtractive color mixing, there's two types. When you mix two or more pigments, you're subtracting the wavelengths that can be reflected, right? When you mix two or more colored lights, you're adding. So remember, pigments are about what will be reflected, right? But we can also change the color or quality of light itself, and that would be additive. So what do we know? Well, then we see in this case that with the subtractive, the blue pigment absorbs most of the light that has the wavelengths above 550 nanometers, right? And notice the chart here. So once we have a blue pigment, these colors are being absorbed, and then the appearance, our experience, our perceptual system is saying, hey, that is blue. But then if we look at the other example, if we look at the opposite, right, then we can see what sections are being reflected, then the yellow. We also have potential for green if we're somewhere in between. So this would be an example of the subtractive. If we want to look at the example of the additive, right, we take three different colored lights, and strangely enough, I mean, this is a weird phenomenon, and this is something that could be tried at home, or maybe you tried it in school, right, in science class, right, probably in grade school or middle school, that you can create white light by combining those three different types of light. So, important to people who study this mechanism in the brain, but equally important to photographers, right? Either videographers and or still photographers. So this additive color mixing then, how do we explain it? Well, the three primary law is explained by the trichromatic theory. Three cones each sense different wavelengths, and if all three cones are activated, then what do we end up with? We end up with the additive mixture and the experience of white. Now, the law of complementarity, explained by the opponent process theory, two neurons associated with each cone are excited or inhibited. So now what the opponent process theory is, some electromagnetic energy, of a certain nature will excite these neurons, but then opposing neurons may be inhibited, so we get this strange process. Let us then take a look at an example here. And what I have is a rather unusual flag. What I want you to do is for 30 seconds, right? And I'm going to let it go for 30 seconds. Stare at this black spot, right? Stare at the black spot.